So this is homework 3 for urban systems engineering, and our group is Kyle and Antonio. So first, a brief overview of system dynamics and its methods. It was created by J. Forster at MIT in 1958. He was inspired by some of the physical laws that govern electric circuits and their behaviors, and he decided to apply these to investigate how high levels of object aggregation flows can be used in system analysis. And really, system dynamics looks at, again, it's a high-level model, looks at broad categories, and it incorporates important structures into the system, such as reinforcing and balancing loops that account for different accumulations and delays. And so there's pretty straightforward method that you use in system dynamics. Once you identify the problem, the first step is to typically create a causal loop diagram. You then add additional information, feedback loops, and data to this causal loop diagram to create a stock and flow diagram. The stock and flow diagram is then incorporated into your model of choice, and you develop a simulation in something like AnyLogic, which is what we used for this homework. So up first, we have the contagious disease spread problem. In this problem, we modeled how an infectious disease will spread through a fixed population. So you can see the causal loop diagram here on the right. And you can see there's a reinforcing loop that goes between the susceptible, exposed, infected, and recovered populations. And this loop incorporates different deterministic probabilities of getting infected, as well as things like a contact rate. There were also incubation times and illness durations that also impacted how this model behaved, and there was no risk of reinfection. So once we had the causal loop diagram, we created the stock and flow system. In this case, we had 4 stocks. There were susceptible, exposed, infectious, and recovered populations. The stocks were fixed to the total population, which is the scope of this system. And you can see from the table on the right of the different values that this was 10,000 people. We then had different flows, which basically represented the number of people that moved from one state of the disease to the next. So the infectious people reinforced the exposure through the loop, because as more people were infected, the exposed people were subjected to an exponential growth as well. So this slide shows the visual representation of our stock and flow diagram in AnyLogic. Again, you can see the 4 stocks as well as the different parameters and dynamic variables that we have going between them. Then this slide shows how the simulation was performed in AnyLogic. You can see that as the model time runs, the different stocks are converted between the different states of susceptible, exposed, recovered, and infectious people. And you can see how those rates and flows accumulate over time. Here's a screenshot of the final plot. We can see that as the susceptible people plot decreases, the exposed, infectious, and recovered people stocks all increase. You can also see that the infectious people stock lags slightly behind the exposed people stock. Again, that is the purple and orange line in that graph respectively. And this is because there is a 10-day incubation period. So people are infected at a delayed amount from when they are exposed. And finally, we performed a parameter variation experiment where we altered the contact rate in the model and then observed how that kind of impacted the different stocks and flows. And you can see from these graphs here that as the contact rate increases, there is a faster occurring and also higher peak in all of the infectious and exposed people stocks. And so this is kind of applicable to the current COVID-19 pandemic, where you can see that limiting the contact rate is actually a very effective strategy for quote unquote flattening the curve or attempting to limit how the infectious disease will spread through the population. Then for some general discussion of the infectious disease model, there weren't any really major difficulties that we encountered when we were modeling this, as this was part of the AnyLogic in 3 days tutorial. So everything was pretty straightforward and easy to follow along with the manual. There were some important conclusions that we could draw from the process. The first is that units need to be consistent throughout the model. The rate should carry the units of people per day per the assigned model unit time. And another thing that we noticed was that you can use other palettes in AnyLogic. So although we were working primarily in the systems dynamics palette, we could also use the plot palette to add our time plots.
Okay, as part of the second problem, we are going to deal with a vast diffusion model. So for this, this is a causal loop. We basically have 2 main stocks, and those are potential adapters moving to an adopter phase through an adoption rate that is in turn affected by an adoption from ads and adoption from word of mouth from current adopters. Finally, you can go back from the adopter phase to the potential adopter state through a discard rate that has to do with the product lifetime. So yes, in general, there are only two stocks, potential adopters and adopters, and those are fixed to a population. In terms of the flows, there are two flows. One that will get you from a potential adopter to adopt to an adopter state, and one that will get you from the adoption to then the potential adopter phase again once the product lifetime is reached. To illustrate this, here we are showing the stock and flow diagram that we did in AnyLogic. And we can see that the discard rate is actually the same as the adoption rate, but just delayed by the product lifetime. We are also going to include demand as a seasonal component later on the model. This is a view at the simulation of the model, and we see that because seasonality is included in the model, then the potential adopters and adopters stocks does not keep a very constant rate. They actually change according to the demand level. Finally, we can see that potential adopters and adopter fluctuate over time as the discard rate lags behind the adoption rate by 2 years. As the major takeaways from this vast diffusion model, the first thing that we can say is that the model time units are a critical aspect for rates and equations in the model. As a second conclusion, we can say that breaking down the model into several simulations while adding complexity is better for identifying mistakes. And that's what we did. We first assume a constant demand and then added that. In sum, we did 3 simulations to complete the whole model.
So then finally, for problems 3 and 4, we were looking at the urban growth model. So in this scenario, we were looking at how a population can further create labor job productions and therefore also impact the creation of business structures. So you can see from the causal loop diagram here on the right, we kind of broke this problem down into 2 separate systems that work together. One was population, which had its own reinforcing loops such as births, immigration, emigration, and deaths. And then this was connected through the labor force and job availability into the business structures and land area available network. And so again, local business structure growth was controlled primarily by land availability and by the demolitions of old structures, which created new land availability. Once we had the causal loop diagram, we created a stock and flow diagram based on the different parameters and reinforcing and balancing loops that we identified. So although there were a lot of variables and parameters, as you can see from this table on the right, we actually only had 2 stocks in this model, as there were only 2 main things that we really cared about keeping track of the number of over time. And so that was population and business structures. For the flows, we actually had 4 flows for the population stock and 2 for the business structure stock. There were immigration and births feeding into the population stock, and then emigration and deaths feeding out to help reduce that stock. Then for the business structures, we had construction rate feeding in and demolitions feeding out. So again, here's a visual representation of the stock and flow diagram that we created based on our different parameters, stocks, and rates in AnyLogic. So you can see we had 2 stocks, population and business structures, with the associated flow rates as described previously, and then a number of different parameters and dynamic variables, and even some table variables as well in this model. So this is a video of our model running the simulation for question 3, which was the growth model. You can see that as the population and business structures stocks change over time, as they approach the end of the 200-year runtime for the model, you can see that they both are approaching exponential behavior near the end of their life. And then this is for the limited growth model, which had dynamic migration. This is for question 4. You can see that around year 50, there's a huge sharp peak in the population and with a sharp decrease after year 50. This also leads to a slightly slower decrease in business structures over time and a slight increase in land availability over time as the model runs as well. So then these are still images of the final plots shown from the previous slides. The model synthesis that we were able to formulate from these conclusions is that as population increases, a corresponding increase in workforce and therefore construction rate leads to rapid construction and land occupation. Eventually, there is no land available and the population growth slows. Now for the bottom row, we are able to see that there are a couple important things that the model can tell us. The first is that immigration is critical for population growth in this community, as the birth rate is lower than the combined emigration and death rate. Therefore, you need immigration in order to have a growth in population in this area. The second point is that the labor availability is driven by population just as much as it is by the available jobs. Therefore, a population decrease will be followed by a job market reduction. Finally, there are some results that we discuss as well. If you're a decision maker, like a politician or something, looking at using this model to examine how labor can change in a region over time, you can notice that the land availability is one of the main constraints for the job market. And so in order to kind of try to limit that and try to disrupt that behavior, you may try to implement some densification policies, such as reducing the land occupied by each business to something under 3 acres, or also promote something like telework, where people are able to stay at home and also work so that you can get more employees for the limited land that you have available. Some other parameters that we could add to the model to increase its scope and try to capture some of the missing behavior could be variation in the fraction of people available to work. Right now, that's set at a static 0.35% or 35% of the total population. You could also include some interactions with other cities, such as commuting behavior between cities. And finally, there's some socio-demographic behavior as well that we can include, such as political policies, crime and violence, and the effect on immigration, as well as infrastructure and environmental constraints as well. So our final answer for model 4 is that as the labor force decreases, the construction rate also goes down. But since the demolition rate is a constant 2% of the business structures per year, the consequence is that the land is cleared at a higher rate than of the construction. And therefore, after year 50 in that limited growth model, you see that the available land actually increases slowly over time due to that demolition rate.
Okay, for the general discussion, we're going to take a look at the major takeaways from the modeling process. For this last model, defining the stocks was kind of difficult just because population is reported as people. And even though jobs can be related to the same unit through the amount of people willing and able to work, it was desired to report back business structures as the unit to explain employment. The chart on the right summarizes the modeling process in AnyLogic and sheds some light into both the population stock and business structures and how they follow a very logical process that at the same time is interconnected between each other. That is to say that in the model, there are some variables like job attractiveness that affect population, but are a function of business structures. For the second part of this model, immigration and immigration change at year 50. To include this variation in the model, time is added as a dynamic variable that affects the now also variable immigration and immigration rates as shown in the picture. With these changes, the simulation is run just like we did before. In terms of the general assessment for this homework, there were 2 major challenges. The first one was to decide what to use as a stock. And then the solution to that was basically deciding what we wanted to keep track of. The second challenge was translating the model from the causal loop to a stock and flow diagram in AnyLogic. Now the solution for that was that maybe if units for a parameter are not constant in volume or in time with the other variables in the model, that gives support to using that specific parameter as a dynamic variable. The favorite part for this assignment was taking a look at the parameter variation experiment. That's a great way to take a look at sensitivity outcomes. The least favorite part is that from a beginner user perspective, a model can get messy. And by messy, we mean that it may have too many links or too many parameters. And that will make it difficult to find errors and troubleshoot. So these are the references we use. And that's it for homework 3. Thank you.